So you are recording this, right, Yusuf?
Yes.
Okay, somehow I don't have the option of recording, so I'll just leave it to you.
How
Uh,
is it possible?
yeah, I don't. It says pause. I guess it's recording. We'll find out. If it's your recording, then we can use that. Okay. Cool. So hi everyone. Welcome back to the second day of this mini course. So let me quickly recall where we ended in the last lecture, because that will be useful for this lecture as well. We saw that there were these point line geometries known as generalized quadrangles, and except for some trivial examples, all of them had an order s comma t, which meant that every line has s plus 1 points, and through every point there are these t plus 1 lines. So this was the order s comma t, and the definition of generalized quadrangle was essentially this one axiom which said if you take a line L and a point X outside that line, so not incident to that line, then there exists a unique line through X. So there exists a unique M which passes through X and meets L in a point. This was the main axiom. What's the useful bit for us, as we'll see later in the Ramsey theory, is the fact that you can't have a situation like this. So you can't have these triangles, these three lines meeting each other pairwise. Okay, so this was a generalized quadrangle, and we saw some small examples, but the main thing that we'll need is infinite families of examples. And the example that I gave you was as follows. This was the example of Arens and Sekerech, which was a generalized quadrangle of order q minus 1 comma q plus 1, where q was a power of 2. So it's an even prime power. And the construction was as follows. You start with the three-dimensional projective space. You take any plane pi in it. So say this, so any plane pi. So this is my plane here in the three-dimensional space. Inside that plane, you take a hyperoval. This was a set of q plus 2 points, no 3 points collinear. Okay. And then the point set of my generalized quadrangle is the set of all affine points. So all the points outside this plane. So that's the q cubed points. And my lines are all the lines outside this plane. So all the lines outside the plane, here it should be pi, such that they meet this plane. So note that every line will always meet every plane in a unique point, or it is contained in the plane. And we take only those lines that meet this plane in the hyperoval. So this is, for example, the intersection point. And we claim that this is a generalized quadrangle. Its order is sort of clear once you look at the definition, but I did not prove why it's a generalized quadrangle. And I thought that it will be nice to at least see this one proof, because in the exercises, you'll have more constructions like this, and you'll be asked to prove that those are also generalized quadrangles. So let's just check the main axiom that we need to check of a GQ. So let's take a line L and a point X not on L. So this is a line of the GQ, so it meets H in this point, and you have a point, a fine point, so outside this plane pi. We need to show that there exists a unique line through X, so a unique line through X that meets L. So imagine this is extended, a unique line through X that meets L, and this line should be a line of the generalized quadrangle, not just of the projective space, so it should meet the hyperoval in a point. So how do we do that? let's just look at the plane sigma, which is the span of x comma L. So the point x and the line L, they span a plane. One way of seeing it is that this is a one-dimensional, this is the one-dimensional vector subspace of the four-dimensional vector space. This is the two-dimensional vector subspace, and this is not contained in the two-dimensional subspace. So it spans a three-dimensional vector subspace, which in the projective sense is a plane, right? Okay, so this spans a plane, and sigma then intersects pi in a line. Okay, and again, you can do this, prove this via simple dimension counting argument, just if you remember the vector space model of your projective space. So we have a line. So if you take this span of x and L, then it meets this pi in a line like this. Okay, and because this is a hyperoval, every line meets this hyperoval either in 0 points or in exactly 2 points. That's what we saw earlier. So there exists a unique point. There exists a unique, so let's say this is y and this is z, not equal to y, uh, such that z is in this intersection and also in the hyperoval. Okay, and now this unique point z will give you the unique line that we are looking for to satisfy the generalized quadrangle, and that line is simply the span of x and z. Okay, so this thing is a plane. So this is a projective plane. And now in a projective plane, which is a linear space, through any 2 points, there's a unique line. So you have this unique line M. And in a projective plane, any two lines meet each other, right? So this line M will meet L. And it's also a line of the GQ. So M is in the line set of the generalized quadrangle, and M intersection L is non-empty. Is that clear? Yeah, just ask any question, because it's good to get familiar with these sort of geometric arguments inside projective spaces. So if anything is unclear, just let me know.
Anurag, can you explain why the line will intersect the hyperoval at 2 points and 0 points? Why not at
So when we saw the definition of the hyperoval,
yeah.
How did we prove that any hyperoval has exactly q plus, or any set of three non-collinear points, any set of points with no three non-collinear points in it has size at most q plus 2? The way we proved it is we picked a point in such a set and looked at all the lines through this point. So there are q plus 1 lines through any point. Each of them intersected it in at most one point. And for equality, you need that the intersection is exactly one further point. That's the reason. So if a line met the hyperoval in, say, 1 point, because these are the only possibilities, right? No 3 points are collinear, so every line meets the hyperoval in 0, 1, or 2 points. If there was a line that met the hyperoval in just 1 point, then you have these q other lines which meet it in one extra point at most, and this gives you that the size is at most q plus 1. But we have a set of size q plus 2.
Right.
That's the reason.
Okay. Yeah.
Yeah.
No,
Okay. Yeah, I should have emphasized that in a hyperoval, every line meets it in 0 or 2 points. Okay. Any other questions? If not, then let's move on. I'll say a few more things about generalized quadrangles, about what sort of parameters the generalized quadrangles can have. And this is, of course, interesting in the study of generalized quadrangles in the theory and the finite geometry world, but also when we will apply generalized quadrangles to Ramsey theory or to other combinatorial problems, it's a good idea to know what sort of parameters are possible because they give you limitations to your methods. So it will come in handy later on. And there's a famous result of Higman, which says that in any generalized quadrangle of order s comma t, s is always at most t squared. And in fact, because the dual of a generalized quadrangle is also a generalized quadrangle, this also implies that t is at most, give me a second, the t is at most s squared. So this already gives you like some limitation. I won't prove this here, but in the lecture notes, there's a nice counting based proof. And that's a really, really nice proof idea going behind this. I think that proof is due to Peter Cameron. And this is one of the limitations. We will soon see some other limitations on the parameters. But most importantly, what are the known parameters for which generalized quadrangles exist? And let's assume s is less than equal to t because you can just dualize and get the other pair. And in this case, all the known parameters are as follows. Q comma q, q squared, q cubed, and q comma q squared, where q is a prime power. So despite 70 or 80 years of research, we only know these particular families of generalized quadrangles. And it's a big open problem to find out anything outside these families or to prove that these are the only possibilities for the parameters. And you will see most of these constructions as we progress in the course because these generalized quadrangles will be a special case of something known as polar spaces that we will see in a few lectures. And also in the exercises, you'll see some parameters. So these are all the parameters we can play with. These are all the infinite families we know that once we start applying them, we know what sort of objects we have at our hand. Okay, finally, to get more restrictions on the parameters, or in fact, to prove some of the non-existence results of the generalized quadrangles, it was useful to look at something known as the collinearity graph of a generalized quadrangle. But for our purposes, looking at this graph will also be useful when we look at Ramsey theory problems. So in the Ramsey theory applications, we will often use what is known as the collinearity graph of a generalized quadrangle. And in fact, this concept can be defined for any partial linear space. So for any partial linear space, you can define adjacency between x and y if they are collinear. So if there exists a line which contains both x and y. This is the collinearity graph. And let's just look for some properties of the collinearity graph in our special case right now. But why is the line unique? Oh, sorry, I just saw the question from the... Oh yeah, that's a good question. I'll leave that as an exercise. Yeah. Because yeah, there is a unique point. You can reverse the process. If there is a line like that, say M, then you can span, you can look at the plane spanned by M and L, and that must intersect the hyperoval in exactly one other point. So it's a bijection between these lines and points of hyperoval. So you can probably do it yourself. Okay, sorry, I missed the chat. Yeah. Let's look at the collinearity graph of a generalized quadrangle of order s comma t. So what can you tell me about this graph? Firstly, can you say that it's a regular graph? Can you say that every vertex in this graph has a constant number of neighbors? So let's just write it. Is it D regular? And if yes, then what is D? Anyone in the chat, or just unmute yourself for a second. Yeah. Yeah, it's fun to make all these mathematicians work on stuff rather than just give a lecture. Approximately S times T, that's a good answer. And in fact, very extremal combinatorics answer. But yeah, you can compute the exact thing as well here. But yeah, approximately S times T is a good answer. Anyone else? Yeah. So indeed, it's S times T plus 1. And the reason is as follows. Take any point of the generalized quadrangle. There are exactly T plus 1 lines through that point, and each of them has exactly S other points on them, except for this point that you started with. So on each of these lines, you get S, so S times T plus 1, right? That's the regularity of our graph. Now, generalized quadrangles have more properties, which we can use to find out an even higher order of regularity in them. So for example, if x is adjacent to y, then x comma y have a constant number of common neighbors. So not just every point has a constant number of common neighbors, any two adjacent vertices, any two adjacent points have a constant number of common neighbors. And again, in the chat, what's this constant? Exactly S minus 1, indeed. So it's exactly S minus 1. Let's just erase the underline. And the reason is, as you would have guessed, if you have two vertices that are adjacent to each other, so say this is X and Y, in the collinearity graph, then that means that there is a line passing through them. And then on this line, there are exactly S minus 1 remaining points. So these are the common neighbors that they have, right? Moreover, there's an even higher form of regularity in some sense. If X is not adjacent to Y, then they have a constant number of common neighbors. So what is this constant finally? Last question. One, T plus 1. So I can see why you would say 1. But how, yeah, Ryan, you know what SRGs are, so yeah, that makes sense. But if you have X and Y, which are non-adjacent, then 1 probably comes from this understanding that if there is a line through Y, somehow I can't go back. If there is a line through Y, then there exists a unique line through X meeting it, so that gives you one common neighbor. But in fact, for each line through Y, there is a unique common neighbor. So if you fix X and Y, then for all of the T plus 1 lines through Y, there is a unique point on that line, which is a neighbor of X in the collinearity graph. So indeed, the answer is T plus 1. And that leads to this. These sort of graphs are quite interesting, and they have been well studied, and they are known as strongly regular graphs. So a strongly regular graph, or an SRG, has parameters n, d, lambda, and mu. I'm going to overuse lambda quite a lot, so I hope it's clear from the context. These will sometimes be eigenvalues, sometimes some combinatorial parameters. I was too lazy to come up with new parameters for different things. Okay, so these are graphs which have n vertices. They are d-regular. Adjacent vertices have a constant number of common neighbors, which we call lambda, and non-adjacent vertices have another constant number of common neighbors that we call mu. And we just saw that the collinearity graph of generalized quadrangles are strongly regular. But there are, of course, many more examples. And for a start, we can look at Kn, the complete graph on n vertices. This is strongly regular, right? It has, well, degree n minus 1. And yeah, it's strongly regular, but yeah, depends on what, yeah, maybe some people might say it's not. So the number of common neighbors of two adjacent vertices is n minus 2, and there are no non-pair, there's no pair of non-adjacent vertices. Let's just say that's 0. Yeah, right. It might be a good idea to say that the graph is, this parameter is undefined, but it's okay. In fact, you can take copies of these complete graphs. So if you take Kn, and so on, if you take disjoint copies of these cliques, then that's also a strongly regular graph. And now we do have non-adjacent vertices, and they have exactly zero common neighbors. Okay, any other examples? Just think of some trivial examples. Anyone in the chat? Maybe Ryan? Of course, I've just drawn one example here. Empty graph, yes, again. Cayley graphs of abelian groups, that's a good guess, but it's not always true. Bipartite graphs depends what sort of regular bipartite graphs. Yeah, exactly. Balanced complete bipartite graph. That's a good example. So K, n, comma, n. And this is a graph where you have all the edges in between, size n, and this is strongly regular with parameters 2n, and the degree is n. Any two adjacent vertices have exactly 0 common neighbors, and and any two non-adjacent vertices have exactly n common neighbors. Paley graph is a very good example. I'll get to that. Abhishek said Cayley graph of abelian groups, those are regular for sure, but strongly regular requires some extra conditions on those Cayley graphs. Yeah. And then, of course, the graph that I have drawn here, the Peterson graph is a nice example. Vertex transitive graphs, again, those are regular, but not necessarily strongly regular. But there is a stronger notion of transitivity in some sense, and that can give you strong regularity as well. Yeah. So in fact, many examples of strongly regular graphs come from group theory. Cycles, okay, I'll write that before the Peterson graph. Not all cycles are strongly regular, but in fact, if you take the 5 cycle, then this is strongly regular with parameters 5, 2, 0, 1. And the 4 cycle is already covered in this previous example, the KNN. Is every Kneser graph strongly regular? I'm not completely sure. Probably, maybe someone else can quickly answer that, but I'll have to think about it a bit. No, yeah. I guess there are more intersections possible. Yeah, but this is an example of a Kneser graph, if you know what those are. And this is strongly regular. This is known as the Peterson graph, and you have the parameters 10, 3, again 0 because no two adjacent vertices have a common neighbor. So say you take these two adjacent vertices, they don't have a common neighbor here. And 1. Any two non-adjacent vertices here have a unique common neighbor. Okay, thanks, Yuval. Okay, so we have plenty of examples. We also saw that generalized quadrangles give you strongly regular graphs, but we will see later on in the course other finite geometries, other partial linear spaces that give you strongly regular graphs as well. So there are plenty of examples. And maybe before moving on, I should give the example which was mentioned in the chat, the Paley graph. Yeah, let's just mention it because I was anyway going to mention it somewhere. It's going to be important. So let's just write it here. Oops. Yeah. So the Paley graph, I hope the spelling is correct. Here the vertices are elements of FQ. So this is my vertex set, Q odd, and X is adjacent to Y if X minus Y is a square. Very, very famous algebraic graph. Yes, that's a very good point. Q congruent to 1 mod 4, because otherwise it's a directed graph. It's not a graph. Yeah, nice. So this is a strongly regular graph. Maybe it's there in the exercise somewhere. Anyway, this is a strongly regular graph. I won't write down the parameters. I can write down the parameters maybe, and then you can prove it. If I make a mistake, then correct me, but I believe something like this. Maybe. Yeah, I'll have to think, but they are roughly equal for sure. Yeah, I think these are the parameters. Okay, so this is also Q minus 5 over 4. Okay, thanks. Exactly. I was worried about that. Yeah, Q minus 5 over 4. Yes, probably correct. If Sebi is saying that, it has to be. Yeah. Okay. Yeah, so these are also strongly regular, and we'll see plenty of examples. Now, we will, yeah, it's a good idea to understand some properties of the strongly regular graph, of an arbitrary strongly regular graph. So let's just quickly go through some of them. I won't prove all of them because I'm sure you can also do it once you have seen the definition. So the first property is that this parameter mu, which was the number of common neighbors between two non-adjacent vertices, is always between 0 and the regularity d. And these boundary cases are sort of trivial. So these are known as trivial strongly regular graphs. In fact, if mu is 0, then you can prove that the graph looks like this. It's a bunch of cliques of size d plus 1, and there are no edges in between. And in fact, if mu is equal to d, in that case, you have the complete multipartite graph where all of these are size d plus 1. So you have d, no, actually not. Yeah, that's that, but yeah, these are not sized. Yeah, no, these are not sized d plus 1. Okay, so whatever the sizes are, but they are all equally sized. So multipartite graphs with equally sized parts, they are also strongly regular. And in this case, mu is equal to the regularity of the graph. So these will be the trivial cases. We'll mostly ignore them. And you should observe that this multipartite graph is in fact the complement of the first graph. And this is not a coincidence. The complement of any strongly regular graph of parameters n, d, lambda, mu is also strongly regular with these parameters. You don't need to remember, but just, yeah, you can prove this easily from just the definition. But yeah, taking complements preserves strong regularity. And finally, what Ryan had said in the chat, that you can use this equation between the parameters to compute one parameter if you know the other three and you know that it's a strongly regular graph. So these parameters of the strongly regular graphs are not independent of each other. And this I can maybe sketch. How do you see something like this? So fix a vertex x of your strongly regular graph and count all possible pairs y and z such that x is adjacent to y, y is adjacent to z, and x is not adjacent to z. So this is not an edge. Fix a vertex, count all of these pairs, y, z, and then when you count it from one side, so when you first pick all possible values of y, you will get the left-hand side, and when you pick from the count from the other side, you'll get the right-hand side. So that's a very easy double counting proof to show that there's this nice relation between the parameters. All right. But the main thing that we will use to understand strongly regular graphs, and in fact, many other graphs that we will see in this course, is the so-called spectral method. So this is a very, very powerful technique in combinatorics in general, and graph theory, where whenever you have a graph, you can define a matrix corresponding to the graph, and then you can use some linear algebra. You can use properties of this matrix to derive the properties of the graph or to study the combinatorial problem. It's a very broad, powerful technique. I will just introduce the bare minimum that we need for our applications, but of course, you should go ahead and read about this if you have never seen something like this before. Okay, so here's the basic thing that we need. For a graph G on n vertices, let's just label them 1 to n, we can define the adjacency matrix of the graph as the n by n matrix where the ijth entry is 1 if I is adjacent to j and 0 otherwise. So we have a 0, 1 matrix corresponding to a graph. For example, if you have, let's say, K4, then its adjacency matrix looks like this. Okay, because pairwise any two distinct vertices are adjacent to each other, whereas no vertex is adjacent to itself. We are not allowing loops in our graphs. All right, and you can do this with all other sorts of graphs as well. And the main important thing to note is that the adjacency matrices are real and symmetric. So if you know your linear algebra, then you know that real symmetric matrices are very well studied. You can really derive a lot of structure of any real symmetric matrix. In particular, you can find out that for any real symmetric matrix, there are these real eigenvalues, n real eigenvalues, if you have an n by n real symmetric matrix. And these are known as the eigenvalues of G. Right? And hopefully you saw it in the review, but an eigenvalue is just any lambda for which there exists a non-zero x such that a lambda such that ax is lambda x. If you have any non-zero vector such that this is true with some real number lambda, then lambda is known as the eigenvalue. And for any real symmetric matrix, you can prove that there are n eigenvalues, n real eigenvalues. Okay. And there are many properties that you can use. And I think in the notes that I uploaded on the website, you'll see some of these things. But an important thing to remember is that the sum of these eigenvalues is always 0 because the sum is equal to the trace of your matrix. It's the sum of the diagonal entries of your matrix. And when you have a simple graph, the diagonal entries are all 0. Okay. This in particular implies that unless in the most trivial case, you should have negative eigenvalues. Lambda n should be negative. We'll see why actually. Okay. Now, there are possible repetitions in these eigenvalues. If you take care of that, if you just write down distinct eigenvalues, and then you look at their multiplicities, so how many times this eigenvalue appears, then a record of this, a tuple of this, is known as the spectrum of G. This is where the name spectral graph theory comes from. So we'll just record these distinct eigenvalues and their multiplicities. Okay. And from the real spectral theorem, which hopefully you have seen in your linear algebra courses, so the n-dimensional vector space, the real n-dimensional vector space, can be decomposed into eigenspaces. So these are EI is just a set of all vectors for which the eigenvalue is theta I, for which AV is theta I times V. And in this decomposition, you see that the dimension of each of these spaces is in fact equal to this algebraic multiplicity, so to speak, or the combinatorial multiplicity. Moreover, EI is orthogonal to EJ for all I not equal to J. So if you take any vector with an eigenvalue theta I and any other vector with an eigenvalue theta j, I not equal to j, then these will be orthogonal to each other. Their dot product will be 0. This is really, really important. And once you know this much, you can actually prove a lot of stuff. So yeah, any questions so far on the basics of eigenvalues? Because now we'll start using them. Yeah. No? Okay. So I hope you could follow this. It was a bit quick. And now we start connecting eigenvalues and these matrices to the properties of our graph. So here is our first lemma, which is quite useful. And it says that for any graph G, if it is deregular, if it is a regular graph, then all of these eigenvalues are bounded between D and minus D. So the largest eigenvalue is in fact equal to D, and the smallest eigenvalue is at least minus D. Okay, and here's a quick proof of that so that you get some flavor of the spectral stuff if you have never seen these things before. Let's see. So say x1 to xn is an eigenvector with eigenvalue lambda. This means that a times x, so say this is x, break in, oh yeah, sorry. Yeah, so we will take a break soon after this. So if you take this equation, then you have this adjacency matrix multiplied by this non-zero vector equal to lambda times x. And now you should observe, yeah, so the proof idea comes from trying to understand what exactly happens when you multiply a vector by the adjacency matrix. So the idea is that the jth coordinate of a times x is equal to the sum of xi in the neighborhood of j. Right? This follows from the definition of the adjacency matrix. When you multiply it with the vector, yeah, all the other entries are 0 except when I and j are are adjacent. That's where you get 1. So this is true. So now to actually prove this, just pick an m such that the absolute value of the mth coordinate of xm is the largest, is greater than equal to xi for all I. So this is a non-zero vector. There exists a non-zero entry. So just pick any index for which this is true. And now you can just use the following, that which is equal to lambda x is less than equal to, yeah, is less than equal to lambda xm. And in fact, no, sorry, right? Ax equal to, no, sorry, what am I doing? Yeah, now let's just look at the mth coordinate. Yeah, so let's just look at the mth coordinate of this equation. So on one hand, you have lambda times xm, and on the other side, you have xi, I inside the neighborhood of m. And now just take absolute values on both sides. And then this is less than equal to d times xm, which implies that, so this shows that all the eigenvalues are in absolute value at most d. And to prove that the first eigenvalue, the largest one, is in fact equal to d, just pick an eigenvector for which this is true. And for that, you can just pick the all one vector. So A times is equal to D times this. So in fact, there exists an eigenvector with the eigenvalue T. Okay. And then this is an exercise for you to show that if your graph is connected, and in fact, it's an if and only if statement, then this lambda 1, the largest eigenvalue, has multiplicity 1. That's in fact a spectral characterization of a graph being connected. And this you should prove yourself. Once you see this proof above, you can just modify it a bit and then you can prove this fact. Okay, so before we move on, yeah, maybe this is a good point to take a break. So if you have any questions so far, just let me know and then we take a break. Any questions? Nope. I don't see anything. So yeah, I guess, should we take a break now, Yusuf? Okay, cool. So we take a 15-minute break now. Yeah. Yeah. So we can already just start using the basics that we have developed for these eigenvalue methods or spectral methods. And let me first try to figure out how to open the chat. Yeah, here. Okay. Yeah. And one of the nice applications of these methods is the fact that for any strongly regular graph, which was defined in a very combinatorial way, you can actually compute all the eigenvalues of this graph. You can give formulas based on just these parameters of the graph that tell you that the full spectrum is something that looks like this. It's a complicated looking thing probably, but the idea is that just from the parameters, you know all the eigenvalues, which of course doesn't happen that often. Usually it can be quite hard to actually determine the eigenvalues of some family of combinatorial graphs that you have with you. And let's just quickly see where these formulas come from and how we can determine the eigenvalues of a strongly regular graph to give you some flavor of this sort of reasoning, which will be useful later on as well. Okay, so the main thing to observe is that the adjacency matrix can be, yeah, wait, let me see or think about this. What's the best way? If you have your adjacency matrix and then you multiply it with itself, so A transpose, which is in fact equal to A square, then this can be written as a linear combination of A and the identity and also the all one matrix. as follows. So let's see what the entries of A square are. Well, if you have the ith row and the jth row and you multiply them together, then what exactly is this dot product? Right? This will be the number of common neighbors that I and j as vertices, what they have, right? Because at the common neighbors, you have both the entries equal to 1, and those are the only entries which will remain. So if I is equal to j, then you just get the degree of that vertex. If I is not equal to j, but it's adjacent with j, then you get the entry lambda, right? Because we had lambda common neighbors. And finally, if in the remaining cases, which is only this one case, you get the factor mu for j minus a minus I, where j is the all one matrix. This is the matrix which has, which just basically tells you the non-adjacencies. From the all one matrix, if you remove the identity, you get the adjacency matrix of the complete graph. And then if you subtract the adjacency matrix, the adjacencies, then you get the non-adjacencies, right? So this is the matrix of in fact, the complement. Okay, so once you have this, you can use this nice equation to actually compute the eigenvalues. Firstly, we know that we have assumed mu to be greater than 0, which implies, in fact, that the graph is connected, and hence d, which was the regularity of the graph, is an eigenvalue with multiplicity exactly 1. So we know that. And if you have any other eigenvalue, say lambda not equal to d is an eigenvalue with eigenvector evec x, which is not equal to 0. Let's just write it in a vector form. Then ax is lambda x, and also j times x is 0. The reason for that is because we saw previously the eigenvalue d corresponds to the all one vector. And because the multiplicity is 1, and from the real spectral theorem where we had this decomposition, if you have any other eigen vector, then it must be orthogonal to the all one vector. And hence the rows of j are just the all one vectors, so j times x has to be 0. Okay, so now if you just use that and multiply this equation, this matrix equation, by x on both sides, then what do you get? You have a square x, which is lambda square x, is equal to d times x plus lambda. Oof, I'm using these lambdas. Okay. Yeah, this was expected. Let's say theta. Let's say theta. And you have also here theta. Yep. Is equal to lambda times theta times x, I guess, plus mu times 0 minus theta minus 1 times x. So you get a quadratic equation. The idea is that because x is the non-zero vector, this implies that the coefficient of x on both sides must be equal because x is non-zero. So this gives you a quadratic equation in theta, and once you solve that, you get these solutions. So you just solve this quadratic equation and you get these solutions, which is some formula in terms of the parameters. Is that clear? Okay. And now I'll erase this just because I want to repeat the argument or do something else here. Yeah. What about the multiplicities? So now we know that there are these eigenvalues, d, theta 1 and theta 2. These two are equations of a quadratic equation, but we don't know what the multiplicities of these eigenvalues are. And for that, we have a very simple argument. Firstly, whatever the multiplicities are, they should all add up to the dimension of your vector space n. And finally, because the sum of eigenvalues is 0, this implies that 1 plus m1 times theta 1 plus m2 times theta 2 is 0. So now you just have to solve these two independent linear equations. And that also gives you m1 and m2. Okay. Why both roots? Yeah, if you have a root, then you can just plug that in again. Yeah, that's a good question. It's an if and only if you have a root of that quadratic equation, and then you just take you have to find maybe an eigenvector or not. Well, it does have real roots. Any eigenvalue must be real, and there must be real eigenvalues. Yeah, I think you don't need to actually come up with an eigenvector. Do we have d rather than 1? Which one? Oh, sorry, that's important. Yeah, good point. Yeah, here we have d. Sorry, the sum of the eigenvalues is 0. Yeah. Okay, so there's this nice method for computing the eigenvalues, and you don't have to remember this, but we will actually need this to show some nice observations about the eigenvalues. It will be a good idea to have a rough idea of what's going on. And I think the main thing that we will require later on is the fact that if lambda and mu, which are the parameters of this strongly regular graph, if they are close to each other, if this thing is really small, say they are equal, which can also happen in the case of Paley graphs, we'll see, then these eigenvalues are in fact square root of this delta, and this is roughly 0. So this is 0, and mu, let's say, is very small compared to k. What's k? It should be d. My bad. It should be d. So what we will see soon enough, that in case that lambda and mu are close to each other, your eigenvalues, this theta 1 and theta 2, are roughly square root of d.
Anurag, is that delta just a symbol or the determinant of?
This delta is this.
Right. So it's just a symbol for that expression, not the
Yeah. So
determinant.
it's this. Yeah, just plug that in there. Yeah. It's just even messier if you actually write down the full thing. Okay.
Yeah.
So the idea, which will be very useful, and we'll see why, is that the strongly regular graphs for which lambda and mu are, these parameters are close to each other, are quite nice. They will be very useful to us. Okay. And for now, let's just see that because we had a generalized quadrangle with parameters s comma t, also had a strongly regular graph as its collinearity graph, you can plug in these parameters that n d lambda mu was equal to s times t plus 1. And I guess, sorry. Oh, I didn't count the numbers. Okay, you can actually count the number of points. It turns out to be something like this. T plus 1, s minus 1, and t t plus 1, I believe. So because we knew these parameters for the collinearity graph of a generalized quadrangle, you can plug all of that in and you get these eigenvalues. The degree s minus 1 minus t minus 1 with these multiplicities. Now, the nice thing about calculating these multiplicities for many families of graphs, in fact, is the observation that these multiplicities have to be integers, right? This is just the dimension of your eigenspace. So these numbers over here, they have to be integers. And that tells you some restriction on the parameters that s plus t must divide times t plus 1. So this is a necessary condition for the existence of a generalized quadrangle of order s comma t. And this sort of thing in finite geometry, this happens quite often, that you use this integrality of the multiplicities to rule out certain parameters for certain finite geometries, but also in algebraic graph theory and spectral graph theory, you have these things like distance regular graphs, which is an even further generalization of strongly regular graphs. There also these sort of multiplicities are quite useful. Yeah, just wanted to mention that. I don't really think we'll need that. It's a neat argument, as Abhishek has said in the chat. Okay. Yeah, finally, the last topic from spectral graph theory that we will need, especially for Ramsey theory applications, is the notion of a pseudo-random graph. And before I define what those are, and my definition won't be very precise either, let's see a very, very nice result from spectral graph theory. So we saw that the eigenvalues of a graph could tell you whether the graph is connected or not. It could tell you many other properties, whether the graph is bipartite or not. Can also be, you can read that from the eigenvalues as well. But this result, which I just write down here, I'll go through it properly. It really tells you a lot about the structure, the full edge distribution structure of any graph for which you know the eigenvalues. And here's what it says. So take any d-regular graph on n vertices such that every eigenvalue other than lambda 1. So note that lambda 1 is just equal to d because it's a d-regular graph. So say all of these other eigenvalues are smaller than lambda, or just take the maximum absolute value of all of these remaining eigenvalues, which you can just write down as maximum of lambda 2 and minus lambda n. This is a positive number. And say this is lambda, then this lambda parameter can actually tell you a lot about the distribution of edges between any subsets of vertices. So take any two sets S and T. These are subsets of vertices, and let E of S comma T be the number of edges, well, the number of pairs X comma Y, such that X is in S and Y is in T, and this thing XY is an edge of your graph. So let E of S comma T denote the total number, not the set, but the cardinality of the set. Okay. And then this lemma says that these number of edges are controlled by this distribution in some way. It says that this number of edges does not deviate from this number, d times the cardinality of S times the cardinality of T divided by n, by too much. Okay. So it gives you both a lower bound and an upper bound on E of S comma T for arbitrary subsets of vertices. That's the important thing here. Okay, and this is also known as the expander mixing lemma, but it predates, in fact, the notion of expanders. Okay, so this will be a very, very useful tool that we will use in all sorts of things from now on. So because it's so important, let's also just prove this. Okay. But before that, let me give you some sort of an intuition about what's going on here. This d times cardinality of S times cardinality of T divided by N is the expected number of edges you will have between S and T if you were just randomly adding edges, uniformly at random with probability d over n. So for every pair x comma y in S and T, if you were just adding an edge with probability d over n, then the expected number of edges will be this. This is sort of like an average or expectation. And this result tells you that E of S comma T does not deviate from the expectation by a lot. And yeah, that's where the random, pseudo-random or whatever comes in. Okay, that's actually a good point. I don't think it matters asymptotically too much, but yeah, d over n minus 1 makes a bit more sense, right? That's the density. Yeah, good point, Alexander. Yeah, it doesn't matter too much. We will be using all of these things in an asymptotic way, so I don't think it matters if you take d over n or d over n minus 1. But yeah, the edge density is d over n minus 1, I guess. Okay, is there a non-regular version? Yes, there is a non-regular version. I'm not writing it down, but you can find that. We won't be using it, but yes, there is a non-regular version also of these sort of results. Yeah. Okay, so let's jump straight in. Let's try to prove this result. And the most intuitive proof that I know of is something I got from Wikipedia. So I thank anyone who edited that page a couple of years back, because this proof was not there before. Okay, so the most intuitive proof is just to interpret this thing in terms of the adjacency matrix. What exactly is this number? What is this cardinality? And then you say that it's at most lambda times square root or whatever. So how do you interpret that? And the main thing is for any subset of the vertex set, you can define this characteristic vector of that subset as the ith entry is 1 if I is in the set and 0 otherwise. So it's a 0, 1 vector that tells you what exactly the elements of S are. And yeah, V is just equal to N for convenience, all the numbers from 1 to N. Now, if you take this product over here, 1 is transpose A times 1, the characteristic vector of another set T, then this is in fact equal to E of S comma T. That's the main thing. So this is the dot product. It's the dot product between the characteristic vector of S and the adjacency matrix A multiplied by the characteristic vector of T. This dot product is just the number of edges between S and T. Okay, and maybe you get it intuitively, but you can try to convince yourself. Once you have this interpretation, you can just translate everything here in terms of matrices, and then we are on to something. Okay, so in fact, this thing over here, E of S comma T minus over N, you can also write this as a matrix, the value, absolute value of some dot product M T, where M is equal to any guesses. You can just check the Wikipedia page if you want to ruin it for yourself. But yeah, tell me what exactly this matrix M should be. And say we already know this, we already know this interpretation, even if you are not convinced or you don't know how to prove this, but say we know this already. D over n times I, that's a good guess, but in fact it's J, yeah, exactly. This is equal to A minus D over n times the all one matrix. Yeah, you want all pairs S comma T, not only those pairs where some element of S is equal to some element of T. So this is the all one matrix that we saw before. Okay. Yeah. And once we have that, we can just try to bound that dot product, right? So just use Cauchy-Schwarz. I keep getting the spelling wrong. Some sort of a Schwarz. Yeah, just write it in a horrible way so that you can't read it. Just apply that, and then you get that this value over here is less than equal to the norm of the vector S multiplied by the norm of the vector M times S by applying Cauchy-Schwarz. And now you already see something happening. This thing is equal to square root of the cardinality of S. Cauchy-Schwarz, yeah. Right? So the norm of the characteristic vector of S, you just sum up all the entries. There are exactly these many entries, cardinality of S many entries, and you take the square root. You take the square and take the square root. It's a 0. So all we have to do now is show that this is less than equal to lambda times, right? Because we already have this factor, we just want the other factor. Okay, so now that's our focus. We want to show that M times the characteristic vector of T has norm at most, or we can just take the squares, has norm at most square times cardinality of T. Okay, that's what we want to show. And how do we do this? Firstly, reinterpret this as, again, the dot product of a vector with itself. So this is 1T transpose times M transpose M times 1T. And now M is a symmetric matrix. So this M transpose is equal to M. So this is equal to, in fact, the dot product M square times 1. So you have to show that, in fact, you can write it as a dot product. Maybe that helps. So you have to show that this thing over here is at most lambda square times cardinality of T. And yeah, there's a T here. Okay. And you already start seeing, once you, that's why I like this proof, you start seeing the proof already that if M square is there, then yeah, it's lambda square can hopefully appear somehow when you apply it, when you multiply it with some vector. Okay. And now note that the vector, the all one vector, and you can divide it by, yeah, multiply it by, let's just write it nicely. 1 over square root n, 1 over square root n, and so on, is an eigenvector of A and J with eigenvalue D. So it's a common eigenvector of both of these matrices. right? And it has, yeah, multiplicity we don't care about, but yeah, for J, it has multiplicity exactly 1, I believe, yeah. So any other eigenvector is in fact orthogonal to this vector for J. And now also observe that A times J is equal to J times A. So these are two commuting real symmetric matrices, and hence they have a common eigenbasis. And this is again a fact from linear algebra. So you can write a nice eigenbasis here. And maybe I should have taken more space for myself. So I can probably erase some things rather than going to the next slide. Okay, we just want to show this. Okay. So now let this be the vector v1. Let v1, comma vn be an orthonormal basis. Eigenbasis of both A and J. Then the eigenvalues, okay, you can just write down that m times v1 is in fact 0, and m times vi, so here let me write it down again, is equal to lambda I times vi for all I greater than 0 or greater than 1. And now what you do is write down this characteristic vector of T as a linear combination of these vectors. Because ultimately we want to apply the matrix M to this. And we do know that the matrix M, when applied to Vi, just gives you the values lambda i's, right? And AI is nothing but the dot product of this with Vi. So M times this thing over here is just 0 plus lambda 2 times 1 comma 1 t comma vi times vi. All right. And now all you have to do is take the norm and you get your thing is less than equal to, or take the square of the norm. So the dot product of this with itself, note that this is an orthonormal basis. So Vi is orthogonal to Vj. And then you get that this is less than equal to lambda square times the cardinality of T. That's the idea. So you can do a lot of these calculations yourself. The main idea is to interpret this thing over here in terms of some matrix product. Okay. So any questions about this? Yeah, maybe this was a bit fast. Nope. Okay. So once we have that expander mixing lemma and this intuition about the edge distribution, we can talk about the so-called ND lambda graphs. So these are just d-regular graphs on n vertices where all the eigenvalues except for the first one have absolute value at most lambda. And the expander mixing lemma that we just saw gives you a statement about the edge distribution between any two sets of vertices in an ND lambda graph based on this parameter lambda. Right? So let me just copy this again and write it here. So we have this lemma, right? And if you remember the interpretation, then you want for all, oh, greater than equal to 2. Good. As Yusuf said, it's good to make some errors so that people can correct them. And yeah, once you have this interpretation, you observe that, so this will be my vague definition of what a pseudorandom graph is, because if you know what a random graph g of n comma p is, where you have n vertices and you pick each edge with probability p uniformly at random, independent of each other, then you can also write down an equation similar to this, where this thing will be the expected value and this will be the deviation, basically. So you can write down an asymptotic statement there, which looks somewhat like this. And p is d over n. Then in fact, the left-hand side would look exactly like this. And then this parameter lambda sort of controls how far your edge distribution deviates from the expectation. So if you don't want it to deviate too much, in some vague way, I guess, if you want it to be more closer to a random graph, more pseudo-random, then you want lambda to be as small as possible. So what we want, lambda as small as possible. This will be our intuitive idea about what pseudo-random graphs are. So we want ND lambda graphs where lambda is as small as possible in terms of the parameters n and d. And once we ask a question like this, once we see what we want, then it's natural to ask what exactly is the smallest possible value of lambda that you can have, right? What's the maximum amount of pseudo-randomness that you can have? And this is the following lemma, which yeah, I have written it in a more technical form, but what you should get out of this is that lambda can't be much smaller than square root d. So lambda is always at least some multiple, which actually is just a constant and something that goes to 1 when n goes to infinity. But this is the main thing that you should keep in mind, even if you don't remember the technical lemma and thing. So in any ND lambda graph, your lambda is always at least square root d, roughly square root d. So what we will be interested in, and what are the kind of graphs that we will use for Ramsey theory later on, are the so-called optimally pseudorandom graph, where your lambda is in fact roughly equal to square root d. So it is as random as possible. Okay, but before that, I can actually give you a quick proof of this so that it doesn't look like some magical looking thing or something too complex. Just observe that so the trace of a is, let's say a square is sum of lambda I square is equal to d, I guess. Yeah, that's the proof, in fact. So if you take the adjacency matrix A and you look at all the trace of A squared, so if you look at the matrix A squared and sum up all the diagonal values, then that should be the sum of eigenvalues of A squared, and those are in fact lambda I squared, and this is d. So from this, dn. Oops, of course, there are, yeah, okay. So it's an n by n matrix where all of the diagonal entries of A square are just d. So the sum is dn, yeah, sorry. And from this, you can manipulate the equation just to get a bound on lambda. Okay, just to give you an idea that how something like this can be shown. There's a more refined argument by Alon and Millman, I guess, which, yeah, I won't look at really. I don't care about that so much right now. Okay, any questions about this? So these will be the pseudo-random graphs, so to speak, that we will be talking about. And optimally pseudo-random, let me just write down, will be an infinite sequence of n, let's say I, di, lambda I graphs with lambda I is equal to big O, some constant times square root di, will be called optimally pseudo-random. And you will see why they are important soon. Any questions? If not, I can just give you an example, but we will see plenty of examples later on. This is an example which was brought up when I asked you for examples of strongly regular graphs. And we saw that there was this Paley graph with parameters q minus 1 over 2, q minus 5 over 4, minus 5 over 4. And here you can in fact check that your lambda is roughly square root d. So the second largest eigenvalue in absolute terms is roughly square root q. So as q goes to infinity, you have an infinite sequence of optimally pseudo-random graphs. And the same thing happens if you look at certain strongly regular graphs. So this was the discussion I was trying to have earlier. If you have strongly regular graphs, where Paley graph was an example of the strongly regular graph, where these parameters of the strongly regular graph are close to each other or zero asymptotically, because we'll be looking at infinite sequences of graphs. And if this is roughly zero or vanishes almost, then you can see that these strongly regular graphs will be optimally pseudo-random. At least that's the intuition you should have in mind, even if you don't remember the exact formula or whatever. As long as you have any strongly regular graph where the last two parameters are roughly the same, then you have optimally pseudo-random graphs. And these will be the main examples that we will be working with to give some nice results on Ramsey numbers. Okay, to end this lecture, so it's getting tiring, maybe we'll move on to Ramsey numbers and applying all of these finite geometry and spectral methods that we have developed to give some nice bounds on Ramsey numbers or even some constructions. But before that, let me mention a very quick, well-known thing that you can prove about ND lambda graphs. This will also be useful. So if you have an ND lambda graph, G, then you can bound the independence number of that graph by this function. And this is just expander mixing lemma with S is equal to T is equal to the independent set I. So take any independent set I, there are no edges in between. And so E of S comma T is 0. And then you can bound the cardinality of that set I by using the expander mixing lemma. And there's a more refined version of the same of this bound, which is known as the Delsart-Hoffman bound, that says the independence number of any graph is always at most minus lambda n, and here note that lambda n is a negative number, so this is positive, times the number of vertices divided by d minus lambda n, which is d plus absolute value of lambda n. I think I found it very confusing when I saw it for the first time, so I prefer writing it like this. Okay, and lambda n is the smallest eigenvalue, which is negative. So we will be using this result as well. It's a well-known result. You can try to prove the more refined version yourself. For this thing, which will suffice in many of the applications, you can just use the expander mixing lemma. Okay, so I think that's it for the lecture today. And in the next one, we'll start getting into Ramsey theory and some applications of Ramsey theory. But before that, tomorrow we have an exercise session where the sheet is available online. So anyone who's interested, just attend that and we can discuss some nice problems. Yeah, okay, so any questions? Yeah, thank you. Alan Bopanna, yeah, my bad. So yeah, Sebi has mentioned a nice result, which actually gives you a more refined bound on lambda. Yeah. Any other questions, remarks?
I had a question, but it wasn't really related to.
Sure.
It was about the random graph on n vertices with probability p. Is there any analogy there with the infinite random graph, in the sense that somehow these random graphs look similar? Or yeah, I've never come across finite random graphs, basically.
Yeah, okay, so this is where I will use the fact that there are a lot of people from Ramsey theory and extremal combinatorics in the audience. Hopefully someone can give you an intuition, because I'm not really that comfortable with this stuff. So I can't give you a satisfying answer for sure. But if anyone who wants to tell you anything about this intuition, just type in the chat or unmute yourself and yeah, say something.
You can sort of say